Alright, so my name is Drahos, and we're going to get started with the first proper talk of this month's SecDSM. We're doing a little talk, well, rather creatively titled SDR 101. It'll be a bit of an introduction and tool talk style overview of SDR, sort of helping you get set up with the tool chain and realize what you can do and what it takes to get started, both on the software and the hardware perspective. Definitely thanks to everyone who helped me get a working laptop here, because go figure, as soon as I move it from there to here, it doesn't boot anymore. So about me, I am currently a master's student at Iowa State studying computer engineering. My research area is with the Power Cyber Lab in the Electrical Computer Engineering Department, so that's SCADA and ICS information security. So yeah, that Ukraine attack you mentioned earlier, yeah, we can't have a meeting without bringing up that word Ukraine about 12 times. Pretty familiar with that one. During my 4 years undergrad also at Iowa State, I did get a lot of experience in security and embedded systems. And I'm also amateur general. My call sign is Kilo Echo Zero Charlie Delta Tango, and I am president of the Cyclone Amateur Radio Club, call sign W0YI. That's just a ham radio club at Iowa State. So I have a fair bit of experience in radio as well as embedded systems, so SDR is really obviously something I got into through both of those angles. This talk is an introduction to software-defined radio. So what is SDR? So traditional radio is all hardware. Think back, hackers in the 80s and 90s are getting some electrical components, some capacitors, and some inductors to build an oscillator and filters to tune to a frequency. Your filtering, your modulation, and all of this mathematical operations are being done with electrical components soldered or some other way electrically connected to each other, to an antenna, to speakers, etc. You're essentially doing math with electrical circuits. Analog modulation, pretty simple arithmetic, such as just multiplying two signals together. Digital can get a little funky, but at the end of the day, it's just electronics all wired together to model math, and it's not configurable. You'll have very limited configuration based on what the circuit is. You've got adjustable components. You might have some adjustable capacitors or maybe adjustable inductors to sort of tune the circuit to the right frequency. Maybe you can have an amplifier that can come in and out of line, but it's just not configurable. However, everything you're doing with those electrical circuits is to model mathematical operations. Well, we have some very configurable electronic devices nowadays that are quite good at modeling mathematical operations. So software-defined radio just takes your samples from the spectrum, just takes the RF that's around us, collects it and sends it to a computer to process it, doing all that math that used to be done with circuits in software, and you now have incredibly flexible, configurable, software-defined radio. So this talk, as I mentioned earlier, SDR 101, it's not SDR 230, which means we're just going to be doing some SDR basics, hardware, setting up a stack. We're not going to be talking about math, and we're not going to be doing DSP or signal theory or any of that advanced stuff, and you're not going to see any of those crazy flow graphs in this presentation. That is quite complicated, something that I'm only really just dipping my toes into right now, but there's plenty of fun you can have with SDR if you can get the basics going, and that's what I'm going to try to help you guys do today. So SDR is a fairly recent buzzword. It's really come into vogue fairly recently, and that's due to a couple factors. One is SDR is actually one of those things that's fairly computationally intensive even nowadays. It's pretty demanding of your computer, and it hasn't been a thing much since we've got these multi-gigahertz processors screaming away in our laptops every day now. One of the largest, though, factors for why it's become accessible on a hobbyist level is that there's been a slew of products coming out where SDR has become so cheap from a commercial perspective that if you're a company, a vendor producing a product, sometimes it's cheaper to just grab an SDR off the shelf, throw some software at it, and put it out on the market. But then your hackers, your open source guys, got their hands on it and figured out what these companies are doing, like, wait, we can put custom firmware on those, and boom, now it's a hobbyist level, dirt cheap, software-defined radio. So that's what's really brought it into vogue, is the fact that you can go on Amazon and buy a $20 TV tuner that has been rebadged as a RTL SDR, and get into this whole wonderful world of software-defined radio. So the basic operation of an SDR is as follows. It takes a slice of the spectrum around a center frequency. So the size of that slice is the bandwidth of the SDR. More capable SDR, you can take a larger bandwidth and you can see more of the spectrum at once. That's equal to the sample rate, which is something that will come up later, and that's what's computationally demanding because it's all of this math that you're doing, you have to do it every time you process a new sample, and if you're sampling at 100 kilohertz, you need to be able to process all of those, you need to be able to perform all those operations 100,000 times a second. And so your bandwidth of your SDR is typically in the single digits to possibly several tens of megahertz. You're not going to see a 1 gigahertz SDR anytime soon, and below 1 megahertz they start to become pretty useless. But for your RTL SDR, those are around 2 megahertz up to your high-end hobbyist level SDRs like the Blade RF or the Hack RF are around the 20 to 40 megahertz range. Just to give you an idea of how much of a slice it's taking out there. So the center frequency is, well, sort of what you're looking at. So if you're looking at 900 megahertz, you'll take 900 megahertz plus or minus your bandwidth, and that's the spectrum that you can then run your processing on. Those are both limitations of the SDR hardware, and you can also run into a sample rate ceiling based on your processing capabilities of your computer. So once again, for example, talking about your higher end hobbyist gear has higher bandwidth. That's a hardware limitation, and different frequency ranges. At the very highest end of laboratory grade gear, you can go down into the very low megahertz, 1, 2 megahertz, all the way up to, if you're spending lots of money, tens of gigahertz with your SDR. But for your hobbyist level gear, we're typically restricted to VHF around like your FM broadcast radio, 80, 90 megahertz, up to 2 to 4 gigahertz. You can go a little higher depending on what exact hardware you get, and I do have a bit of hardware comparison coming up. And the biggest thing though to keep in mind is when you've taken that slice out of the spectrum and brought it down to do your processing on it, the center frequency, what you've tuned your SDR to, becomes 0 hertz at baseband. So you have positive and negative frequencies happening, which can be a bit to wrap your head around until you realize if you just think of it as an offset, it really makes sense that 0 hertz at baseband, but your SDR is tuned to 100 megahertz. So 100 megahertz. Negative 5 megahertz is just 95 megahertz. And then you're just doing your processing based on wherever the SDR is tuned. So there are several considerations when you're going out to buy SDR hardware. Transmit capability is a huge driver of cost, especially if you're talking full duplex. So there's full duplex and half duplex. Half duplex just means you can transmit, then it has to switch over into receive mode, and then switch back to transmit mode. If you have full duplex, you have simultaneous receive and transmit, which is necessary for something like radar or more complicated digital protocols like GSM or all the crazy cell phone stuff people are doing. You'll need full duplex capability. One thing that's not a concern for SDRs is transmit power. They are all of essentially negligible power, which is great for benchtop laboratory scale experiments. And if you want to go do some dubiously legal things involving hijacking, cellular service over an entire city, you need an amplifier. Don't get any ideas. So the specifications that you're going to see on an SDR is the frequency range, which will be what's the lowest frequency and the highest frequency you can tune to. One thing to keep an eye out for is if they say they can go down into high frequency, which is anything below 30 megahertz, they're probably lying because it's on an electrical level completely different. The Hack RF can supposedly go down to like 100 kilohertz. It's useless below 50 megahertz. They just really don't work down there because you need to design them completely differently. But otherwise, the high end, that's fairly accurate. So, for example, the Blade RF can go up to 3.4, don't quote me on that, it's in the slide later, gigahertz, which means it can cover the 2.4 gigahertz Wi-Fi, GSM band, or not ISM band, but not the 5 gigahertz, 5.8 gigahertz stuff. And so, you know, your frequency range, that's an important specification based on what you want to do. Bandwidth is huge. The more bandwidth, the more of the spectrum you can look at once, and the more expensive it is going to be. And then the resolution of the analog to digital converter. 8-bit is a little crappy. 16 bits is the high end of what's actually practical. Some people go in and quote, yeah, it has a 24-bit ADC. But you need to do some insanely good engineering to actually get anything out of that. So if they're going on advertising, you see a Kickstarter, like, it's got a 32-bit ADC. They're probably lying to you, because that gets into the realm of just this insane high-level RF engineering to actually get anything meaningful from that. So the 12-bit is common, 16-bit's pretty good. 8-bit, like the hack RF transmit is only 8-bit, and it can cause problems because it's just low resolution. And then finally, the most important part of any SDR hardware is what software you can use with it. GR Osmo SDR is pretty critical for a lot of the hobbyist hacker type things. That is the sort of driver wrapper that lets you plug your SDR hardware into the entire GNU Radio framework. Tons of applications people have written on top of GNU Radio. So you'll actually see Kickstarters for SDRs that are like, we already have support for GR Osmo SDR, which means that you can just get their SDR and plug it right into all this stuff that already works. If they don't have support for that, well, either get really good at contributing to open source or buy something else. On a more personal note, I do like some things that are based on SOPI SDR, and they also have a GitHub repo. It's nice to have that because there's some pretty appealing applications that use that sort of framework. So just looking at some hardware here, the RTL SDR, everyone's gateway to SDR. I started off with one, tons of people have them. They're about 20 bucks, receive only, 20 to 2000 megahertz, 3.2 megahertz bandwidth. So you can essentially get your 3 megahertz slice anywhere in the spectrum from 20 to 2 gigahertz. So that includes like the broadcast FM band, which is around 80 to 105 megahertz. And with 3.2 megahertz, you can listen to like 8 radio stations at the same time with one of these, if you are so inclined. The hack RF is also very popular. It's in the $200 to $300 range, depending on what sort of deals you can get. Much more capable. It's really the cheapest SDR that can really do a lot of what you want. It's got very good frequency range, a lot more bandwidth, but it's got some pretty big hamstrings. One, you're paying $200 for a half duplex SDR, so that means you can't like do radar with it, period, which sucks. Or you'll see people doing like GSM, they need to have 2 hack RFs because it's only half duplex. And then it's got the 8-bit ADC, which is just disappointing for how much money you're paying for it. The Blade RF is very high end for hobbyist gear. It's actually what I have here. There's a $400, $650 model. They're essentially identical. Full duplex. It doesn't have a bit of the lower end of frequency range, but it's got twice as much bandwidth. And so just sort of my thoughts on this is that like if you don't have an RTL SDR, like just go get one. It's a $20 toy. They're great. Or you can get a dozen of them. Whatever. They're cheap. The hack RF is easy to start with. It's one of the best starter kits in the market. It comes with a good antenna. It's got a good case on it, but it does have those performance limitations. And the Blade RF has a lot of capabilities for running standalone. So, for example, you can actually load the software onto it itself and do crazy stuff. Like they had one locked in a box, spoofing GPS and making a cell phone run around actual Paris in the Paris Hotel at FCON last year. No computer needed. Then there are always tons of other SDR stuff popping up. The Lime SDR is one recent Kickstarter that actually looks quite good. It checks all the boxes, has great quoted specs. The USRP is amazing. They just destroy everything else on the market. They're the best SDRs money can buy, but you're gonna have to get your boss to buy one. Like When it says email us for a quote, you know you can't afford it. And then finally, you can get SDR development kits for embedded systems. There's several of these from Zboard, like the PicoZ, but they're not for the faint of heart. They're essentially for product development, so it's an option. If you think you're, that awesome, go for it. They're pretty cheap, but it's not an SDR. It's like a 6-month development cycle away from being a plug-and-play product. And then the final hardware consideration is that of an antenna, and I'm not going to get into hardly anything of talking about antennas here because that is just a tremendous rabbit hole. As any of you, if there are any amateur radio enthusiasts in the audience, they will know that you can't just have a 30-minute conversation about antennas. But just watch the frequency range, and especially if you're transmitting. If you transmit into an antenna that is poorly matched for the frequency you're transmitting at, it can reflect power back to your radio and blow it up. And there are tons of resources out there if you want to start getting into building your own antennas or knowing how best to hook up, mount, place, orient antennas. Hams have been doing this for 90 years, so it's not a solved problem, but there are tons of resources out there. All right, so the biggest thing that I want to be able to help you guys with is just getting stuff set up so that you can work with it. I'm focusing on Linux. Windows is a completely other beast, and you also run into some serious limitations when you start talking about going in there and doing real SDR work where you're doing those terrible flow graphs and the horrible math and the really fun stuff. So there's a lot of ways to get everything compiled. You can find some of the stuff in repositories, depending on your distro. Sometimes it's in separate repositories. GNU Radio has this PyBombs utility that scares me and I don't know much about it. I think it's stupid. I just compile everything. It's not that hard to download a Git repo and type CMake, which fortunately is completely ubiquitous in SDR land. Everything has more or less standardized on using CMake. So you're just essentially pulling down Git repo and doing your standard CMake. I usually use the last stable tag on Git and maximize your optional dependencies. Because a lot of your SDR software is using CMake, you can build it without support for certain things, and that can come back and bite you later. Especially if you're trying to run demos or examples. If you are missing a dependency that they assume, you're in for a rough time. So there's some standard sort of software or higher level applications, including standalone receiver software. GQRX is pretty popular. I prefer Cubic SDR. It just looks a lot nicer and it's a lot easier on the eyes and has more information for you. Then there are these sort of platforms which are very modular and they're just a framework for creating SDR applications in. GNU Radio, which GQRX is built on top of, is the de facto sort of hobbyist SDR platform for building custom applications as well as like GQRX runs on top of it. SOAPy SDR is kind of an outlier in the field, but it builds super fast and is really convenient, and it's got a good remote system for running stuff over the network. It's kind of nice. And then that GR Osmo SDR that I mentioned is a hardware plugin. So GR Osmo SDR has like 12 different software-defined radio hardware devices that it supports and then presents those to GNU Radio. SOAPy does a similar thing with a bunch of individual plugins. And then finally, all of this goes on top of your device libraries, which is libUSB or whatever builds on top of that, and that's tied specifically to the exact hardware. When I go to set up an SDR environment on a new laptop, this is the rough process I follow, and I have actually all these steps broken out into appendix slides as sort of a guide if you, and the slides are posted on Slack, so you can go through there and just just go set up an SDR environment on a Linux laptop. So the first thing that you have to build is your device libraries. So if you got like, say, HackRF, you need to compile the HackRF library, and there's usually nothing crazy that you need to do that. Then there's GNU Radio, which is the massive beast. It has some huge dependencies. I've got some of the more problematic ones mentioned at the end, but it's things like the Qt libraries and the WX libraries. are, you have to get them installed, but they're in all of the repos. Debian, Ubuntu, and OpenSUSE all have all the dependencies. If you look hard enough and just type a bunch of package manager installation commands, you'll eventually get all the dependencies. And it takes like 30 minutes to compile. SOAP SDR is pretty easy, and I do it in this order because it parallelizes a little, and you'll hit, like, the new radio gets pretty much all the dependencies you'll need to install anything ever on your system. Liquid DSP is a cubic SDR dependency. It just installs out of a GitHub repo, works pretty well. Cubic SDR, same thing, installs out of a GitHub repo, works pretty well, and you shouldn't have any extra dependencies. Then finally, the specific plugins for SOAP, and then GR, Osmo SDR. And if you go in this relative order when you're installing all this stuff, it just kind of all wraps up and picks up optional dependencies and hardware support well enough. And like I said, there's sort of an installation step-by-step set of slides at the end of this, which is posted in the general channel of SecDSM Slack. Collection of links. So if you want to go back and set up later, this is a pretty good guide. So now let's actually talk about doing some stuff with radio. For audio, I'm not going to get into any digital stuff. It's different. But for phone, audio, radio, essentially the goal is to take an audio frequency signal, which will be in the, say, single-digit kilohertz, like 2600 hertz whistle, and then modulate it, which is some fancy math, with a radio frequency carrier wave. And your bandwidth on audio is either 5 to 50 kilohertz, depending on how high fidelity you want. And there's a couple of different ways of doing that math. So then you've got this radio frequency signal, which you'll amplify and feed it to an antenna, and it'll radiate throughout the universe, where some other antenna will pick it up, apply the same math in reverse, and then you're done. Well, when you're receiving with an SDR, it's a little more complicated because you have to shift it down to baseband. So that signal, it's not like you're tuned to a particular signal to receive it with an SDR. Instead, you're just taking that slice out of the spectrum that contains your signal, shifting it down, because you've taken it down from, say, 100 megahertz down to 0, and then you do your demodulation math in software. So for an example, if you're listening to 105.1 megahertz, that's one of the pop radio stations around here, I think. You might tune your SDR center frequency to 105.0, and now that radio station will show up at 100 kilohertz on your SDR software, and then you can demodulate it from there. When you're working with a software-defined radio, it's important to be able to visualize, oh, that is a GIF, and this is a PDF, and darn, that's a very useful GIF. Whoops. It's important to be able to visualize signals, especially if you're going in and doing some stuff on your own with building a signal chain. So there's two domains that you'll typically think of a signal in. The first one is your time domain, which is what you're seeing on the left, which has the time on the x-axis and the amplitude on the y. And this is, think back to your trigonometry course, like, here's a sine wave, right? Yay! But it's not very useful. Like, what does speech look like in waves moving up and down? It's terribly useless. So the frequency domain is typically what you end up looking at in software. I have some pictures on the next slide. So you'll have your frequency going across the x-axis and the relative power on the y-axis. So the more power at that frequency, the stronger, the louder that frequency is relative to the other frequencies, the higher it is. And this will either show up as your straight FFT where you've got a graph, or as a waterfall where a stronger color means better. And that's nice because your waterfall can show you how that's changing over time. And the waterfall is definitely what people think of when you wonder what a signal looks like. And then finally, those three types of modulation with some lovely GIFs that are not animated. AM, you're just simply multiplying the RF carrier with the audio signal, and the amplitude of the RF equals the amplitude of the audio, And it works, you can see there that top signal is your audio signal, the middle signal is AM, and you can see how it outlines the signal there. With frequency modulation, it's a little more complicated. The amplitude is constant, but when your signal gets to a lower amplitude, the frequency of the frequency modulation goes a little lower. When it gets to the peak of the wave, it squishes together, goes to a higher frequency. In this sense, you have a center frequency for your FM that you then deviate from based on the amplitude of the AM. And then finally, one thing that's very familiar to any ham radio guys in here is single sideband, which is literally taking half of the AM signal, either the lower or the upper, and it's half the power, so you get more efficiency. You're not sending the same information out with a mirror image of itself, and it's not that much harder to decode. These are what those look like compared to each other. On the left, you have amplitude modulation. In the middle, you have the single sideband, which is half. There are different signals, but essentially it's the upper half of the amplitude modulation. And then there's the frequency modulation. One important thing to sort of notice here is that with AM or SSB, you can really see what's going on. You can see like there individual lines which represent individual frequencies that are particularly strong at that time. And you can't visually see that sort of information with frequency modulation because it gets twisted and 90 degrees and it's hard to see. But with single sideband especially, you can really see what the audio looks like and see certain frequencies are stronger than others. I don't know what's actually happening there, it's probably voice. Music is a lot cleaner in single sideband. So if you're looking at your SDR receiving software, this is a screenshot of Cubic SDR, and this is your, in a sense, control center for using the SDR. You have certain types of modulation that you can use, but the main waterfall is by far the largest feature of any SDR software. And it's showing you, well, across the x-axis you have frequencies going from, in this case, 97 megahertz up to 104 megahertz, so the middle of the broadcast FM radio band. And you can see various signals there. They have a strong center frequency, which is your very well identified, I guess I can gesture with this. Strong center frequencies, and these are radio stations. And then, deviating off to the sides, you can see where your data is actually at. And then to use this software, you just simply click to drop a demodulator on there, and then you can listen to that radio station. Your different modulation types, I guess, are listed out. It supports FM, which is meant for your 200 kilohertz bandwidth broadcast FM. It's much wider deviation, it's a much higher fidelity sound. Narrowband FM is what you'll see for like walkie-talkies or amateur radio, and it's much lower fidelity, but it's good enough for voice. To carry human voice, you only need about 5 kilohertz of bandwidth. It'll work perfectly fine. AM, you can either get broadcast AM, Voice of America, that sort of thing, or ham radio, AM, not as common as single sideband. And then finally, upper sideband, lower sideband, very commonly used by ham radio. Double sideband is essentially AM with a suppressed carrier. And there's plenty of resources out there for learning about these, but you choose the modulation that you think is most likely based on where it is in the spectrum and what it looks like on the waterfall, and then you click to drop a modulator on it. You have various other tools up there. You have frequency selection where you can choose that center frequency to determine what slice of the spectrum you're seeing on the waterfall. The bandwidth within the capabilities of your SDR can be adjusted. And that's essentially just a zoomed in waterfall there to help you finely adjust to get your tuning right on. And receiving with Cubic SDR and GQRX, and on Windows, SDR Sharp, all very similar to this. You just choose the center frequency. You can observe any signals that are within the bandwidth of that center frequency, close enough to it that you can see them. Click on one to drop the demodulator. Figure out what sort of modulation you're supposed to be using to listen to it. Get the bandwidth tweaked right. If your bandwidth is too big, you might get some extra noise. If your bandwidth is too small, it might clip, etc. and then you're listening to a radio station. And then just kind of leaving you here with some other radio concepts that you might run across if you start playing around with software-defined radio. Gain, there will be gain adjustments throughout. So gain is just amplifying the signal, however it also amplifies the noise. And so, you might think, oh, just turn the gain all the way up. No, that's a trap for young players. You don't want to be doing that, especially if it's in software. It just gets messy. When you're looking at SDR, there's typically one or two amplifiers on the receive side, which are hardware amplifiers that can be tweaked from within the software. That's what, on the screenshot, those gain, manual gain controls in there adjust the actual hardware gain. So those are tunable circuits within the hardware that the software can adjust. And then you do have unlimited gain in software, but that gets very messy very quick and doesn't typically help you hear anything. You might also see references to audio frequency gain. That's just volume. We pretend we're cool by using words like that. Squelch is also another thing that comes up. If you haven't played around with walkie-talkies, squelch just mutes until a signal is received. That way you're not listening to a bunch of noise. If you're not hearing anything, see if there's a squelch checkbox and tweak that. GQRX is infamous for, at least in my experience, you mess around with it forever, realize it's just because it's not breaking squelch. Disable that and all of a sudden you're hearing it. Or of course, if you're sick of the roaring static in your ears, squelch might be a very good idea. So how can you take SDR and sort of run a little further with it? Well, you can get into GNU Radio or GNU Radio Companion, GRC, and creating those flow graphs of signal processing. If you decide to go that route, there are some things. I can't provide a full introduction to GNU Radio and flow graphs in 30 minutes. But you're essentially going to need to pay attention to having your sources and your sinks all wired up to each other. And you don't have to use real hardware as a source or a sink. I actually did a lot of my learning and experimentation, and there are some tutorials where you're just taking audio from a WAV file, or even just generating a signal entirely within GNU Radio, and then using a modulator or some filters and throwing a bunch of waterfall graphs at it and seeing what happens to the signal as it processes. This is a very good way to learn how to experiment with this. When you start doing custom SDR stuff, the number one, number two, and number three issues are sample rate, the sample rate variable, and sample rate. You'll run into computational limitations where you just can't handle the processing at a higher sample rate. I haven't been able to find a laptop that can handle a decent amount of filtering at above 100 kilohertz. You also run into hardware restrictions. Your sound card and your SDR will only like certain sample rates. Sound cards, especially integrated ones, will have 5 sample rates that let you set. Anything else will throw errors. And SDRs also might work like that as well. And then WAV files also have a specific sample rate. If you read from WAV off the wrong sample rate, it won't sound right. And learning how to convert those, very useful if you're just creating test signals that you want to transmit. So, all these things can go wrong with it. There are easy ways to convert between sample rate, but they have all of their appropriate gotchas. Decimation, so first off, happens in integers. You can't multiply. Say you've got a 5 megahertz sample rate and you need to go to a 7 megahertz sample rate, you're going to have to do some math. You can reduce sample rate by integers or increase it by multiplying by an integer. When you do that interpolation, you'll get a bunch of echoes throughout. It gets a little ugly. If anyone wants to talk to me later about that, I have a great case study in fighting through that trade-off. So just a typical example of what you'll have to do for your sample rate conversion. You might have a 44.1 kilohertz sound card with a microphone in it. Say you just want to transmit. Then after doing your frequency modulation, it'll come out at double that sample rate. You'll do your filtering at that sample rate. And then the last step is cranking it all the way up to 5 megahertz to feed it into your software-defined radio. And right before you feed it in, you can do a frequency shift, which has to be done at the final sample rate. So just sort of, as it's going through that chain, the sample rate will be changing, and you'll have to go through and count everything up to make sure it's right, which is one of the biggest gotchas. So you do have to watch the variable types in GNU Radio. There are floats and complex. Floats should only be used for audio, otherwise you're going to have weirdness. And you can have underflows or overflows. go through and check your sample rates, and there are some other gotchas in there that have given me quite a bit of pain in the past. And then finally, although the software itself very much yells at you if you don't use Drahos correctly, and then a bit of an issue is sticking with one graphical system. GNU Radio supports 2 WXMPT. And examples are a pain in the ass because they'll do it with a different version where the block will have a different name and it'll be missing, or it might have an extra variable that they don't assign. Pictures actually tend to be a lot easier to work with than actual GRC files, especially when you're just getting started. The last thing you want to deal with is trying to load up an example where the block has a different name than it does in your version of the software. Plus, pictures just give you a nice overview of sort of how it flows through. I have some resource slides at the end. There's some great tutorial PDFs out there. The first one is pretty basic, just shows you how to put together some chains in GNU Radio. And the second one has some very good concepts of like what SDR is. It's from the people who make that USRP. Some of the labs are dumb, but goes over using the instrumentation, the software instrumentation, such as waterfalls, oscilloscopes, and other ways of looking at your signals. And then that last one is sort of a blog from one of the core developers for GNU Radio, and does lots of stuff with math, if that's your thing. And then just some radio resources. The Signal Identification Wiki is wonderful for seeing what certain weird things look like and sound like. And FLDigi is the universal standard for software for doing ham radio digital stuff. So if you're messing around down in the listening to the amateur radio bands and you hear weird beeps and sounds, FLDigi can probably decode it for you. And then a couple of links to antenna resources if you decide to go that fun route of building your own antennas out of tape measures and wire. End of the slide has those installation steps broken out. I really encourage you to just pick up one of those RTL SDRs and start listening to radio stations. If you can get a good software chain built up, which is not the easiest thing to build right now. It's getting better, but if you're comfortable installing from source, just go through and do that. And as soon as you start playing with it, you'll see how much you can do, and next thing you know, you'll be staying up late at night doing a bunch of math and flow graphs. Any questions? Any comments? I'll even take insults. Thank you.
You're too smart. Thank you for presenting. As a token of our appreciation, I'd like to present you with a SecDSM shirt. It's a large.
Perfect. That is my size.
We're gonna take like a 5-minute break and then jump right into the next presentation, which is Kelsey with data breaches. So 5 minutes back here.